So we've done characteristic 1 already, which was looking at the non-permissible values. So right now, we're looking at equations that are rational functions, which has some sort of polynomial in your numerator and another polynomial in your denominator. So in this one, you're dividing by x minus 3 and x plus 1. Your non-permissible values are 3 and negative 1. Now, we are on 106. Perfect. So with this, those non-permissible values either turn into vertical asymptotes or holes. And the key thing is whether or not the factor simplifies away. When the factor does not simplify away, like in this case, you can't cancel out the x minus 3, you can't cancel out the x plus 1, you will always get vertical asymptotes. If the factor cancels out, like in this one, these x minus 3's would simplify, you still have a non-permissible value of 3, but then that becomes a hole in your graph. So after it cancels out, you now have a new simplified equation, but you still have a non-permissible value of 3. And when you plug in 3 into this line, you would get the point 3 comma 4. So that becomes a hole, and you know where the hole is. So whenever a non-permissible value or a factor cancels out, you still have to remember that it was a non-permissible value. But you graph the new graph, the simplified version, and add the hole into that new graph. And sometimes, in this case here, we have one of them cancel out, but you're still left with another x minus 3 on the bottom, then you'll still have a vertical asymptote. So whatever non-permissible values are left at the end of your simplification, they will stay vertical asymptotes. If a factor canceled out that isn't there anymore, then you'll have a hole in your graph. So that's characteristic 1, and I'm going to write out, after we go through characteristic 2, I'm going to write out sort of steps that we're going to use to follow when we're graphing these rational equations by hand that will help us sort of do things systematically. So characteristic number 1, we will do example 1 after we go through characteristics 2 and 3. After finding holes and vertical asymptotes, we then start to look for oblique asymptotes. So there's sort of 3 different situations for oblique asymptotes. This one, situation number 1, if the degree is larger in your denominator, so in this case, the highest degree in this equation is an x, it's larger in your denominator, we have no x's in our numerator. You will always have a horizontal asymptote and it will always be at y equals 0. Situation number 1, the degree is larger in your denominator, so that can appear like this, a 1 over x graph. It could appear as an x in your denominator, an x in your numerator, and x squared in your denominator. Whenever the degree is larger in your denominator, what's happening as your x values get really, really big is that your y values will always get really, really small. So a characteristic about horizontal asymptotes is they tell you what happens at extreme values for x, either when x gets to very, very large numbers or when x gets to very, very large negative numbers. And if your denominator has a higher degree, for example, if I plug in 1,000,000 into x plus 1 and 1,000,000 into x squared minus 3, x squared minus 3 is going to be way, way bigger than x plus 1 because that power of 2 makes it that much bigger. And so I'm going to be dividing by a very big number, and anything divided by a very big number gets really, really close to 0. So in this situation, if you notice the degree is larger in your denominator, you can just say, boom, I know that we're going to have a horizontal asymptote at y equals 0. Second thing that could happen, degree is the same. So time number 2, I find the textbook's explanation a little bit over the top, so we'll simplify it a little bit. So 2, when the degree is the same in the numerator and denominator. Again, and I'm going to just write y equals the coefficients. And what do I mean by that? Well, in this one, 2x minus 3 over x minus 1. First of all, we recognize the highest degree is x, a degree of 1. There's an x in your numerator, there's an x in your denominator. The horizontal asymptote in this one is going to be y equals 2 over 1. The coefficient of the x on the top, the coefficient of the x on the bottom. In other words, y equals 2. They go into a synthetic division remainder thing that we do not need to know, so you can ignore that. It's that simple that it's at y equals 2. The reasoning behind it, again, at extremes. If I put in a very, very large number for x, subtracting 3 really isn't going to make a big deal, right? You have $2 billion. You lose 3 nickels. Who cares? Right? On the bottom, you have $1 billion. You lose a nickel. Who cares? Can't use pennies anymore because don't know if there might be somebody in class that's never even seen a penny before. But yeah, it doesn't make a difference. And so you can basically ignore the minus 3 and the minus 1 and say, well, I have double on top and 1 on the bottom. It's going to be really close to 2. Really close to 2 times the amount. But because there is that little bit extra, your graph gets really close to that, but never quite equals it perfectly. So we've had 2 of the situations, degree bigger in our denominator, degree is the same. What haven't we talked about? Situation number 3. Situation number 3. Situation number 3, the degree is larger in the numerator. And this is when we get the diagonal asymptote, or the oblique asymptote. And here we have to use synthetic division to find it. So if we had, and we were attempting to graph x squared over x plus 1, if I divided x squared by x plus 1 using synthetic division, it would look like that in the red box. You'd have to add zeros for the things that are missing. You're dividing by x plus 1, so you put a negative 1 outside. Bring down the 1, multiply, add, and you get x minus 1 with a remainder of 1. I'm going to tell you right now, from there, you can ignore the remainder. It doesn't even matter if the remainder was 17 billion. You could still ignore it. And whatever you get as the value, that becomes your oblique asymptote. So in this case, the oblique asymptote is y equals x minus 1, which is a diagonal line, and you would draw it just like we would draw things. Here's the picture. Oh, they don't have a picture for us. Really? No, they didn't. Well, we'll draw it when we get to our examples. So this section, section 2.3, the questions all break down to be little characteristics, but what we're going to do just to practice is we're going to practice graphing right from 2.3, because that's supposed to lead into 2.4, and this is our last thing to be able to do in this unit, to be able to graph all different functions. So when we go back to example 1 here, the question says, use the equation of each function to figure out if there's a whole or vertical asymptote. We're going to do that, but we're also going to graph it completely. Yes?
Can you go back a second?
Yep.
Like in the synthetic division,
Yes?
you know which, it's X takeaway one, but which, like, is it the second number you get, or?
Well, if you wrote your division statement, right, I'll put a box around it. Here would be the division statement, one form of it. Okay? And with that, okay, I'll write the division statement out properly. Okay? Your equation, if you're doing x squared divided by x plus 1, the division statement would say that x squared is equal to x plus 1 multiplied by x minus 1 plus the remainder of 1. Okay? This is the division statement. This is actually a really good question because the exam sometimes asks for the division statement in another form. The division statement that we've learned all the way through is the polynomial is your divisor multiplied by your quotient plus your remainder. If you divided everything by your divisor, if I divided everything by my divisor, this is what I would get. The reason this is important is because now I can rewrite my original equation was x squared over x plus 1, right? Because x plus 1 is my divisor. And here, the x plus 1s would go away. So I would get equal to just x minus 1 plus my remainder is 1 over x plus 1. Okay? That is another form of the division statement. It's one, so it's written this way, P divided by D equals Q plus R divided by D. It's just a rearrangement of this one by dividing both sides by D. And if you write it that way, you can ask yourself, and you can say, what's going to happen to this side as x gets really, really big is going to be the same as what's going to happen on this side when x gets really, really big. Does that make sense? Like, if I make x really, really big on this side, and I make x really, really big on this side, since they're equal, the same thing should happen. And on the right-hand side, if I make x really, really big, can you see that this last term, 1 over big number, will be 0? And we just get x minus 1. And that's saying that that's why we have an oblique asymptote at x minus 1. Because as x gets bigger and bigger, it gets closer and closer to x minus 1. So we have three situations. To recap them. Situation number one, the degree is larger in your denominator. You recognize that, boom, you've got a horizontal asymptote at y equals 0. Situation number two, the degree is the same. Then you've got a horizontal asymptote, and it will always be at the coefficients of the highest degree. So in this one, it was 2x minus 3 over x minus 1. Your horizontal asymptote is going to be at 2. I'll give another example. Let's say the top is 8 minus x minus 8x cubed over x squared plus 3x cubed. This one has a horizontal asymptote. I tried to mix it up to make it appear more difficult, but it's not. The highest degree is the x cubed. So your horizontal asymptote will be at y equals negative 8 over 3. I take the coefficient of the highest degree there, the coefficient of the highest degree that matches, and that's your horizontal asymptote. And number 3, when the degree is larger in your numerator, you get an oblique asymptote. So now if we go back and do example number 1, what we're going to write off to the side here, we always deal with characteristic 1 first, characteristic 2, then we sometimes need some additional points. So step 1, find all vertical asymptotes and holes. Right? We do that using our non-permissible values. Okay? And if you're going to have a hole, your equation simplifies. So as an additional note here, we will be always graph the simplified equation, because you will get some situations where, and it's perfect, example 1a does it for us. They're so nice, so kind to do this for us, where if you skip to step 2 and try to do step 2 first, you're going to run into problems because you're not graphing the simplified equation. And example 1 is going to show us that. Really nice of them to be so considerate. Step 2, find our horizontal or oblique asymptotes. And for our situation, it's going to be or. We're not going to have, I guess I can take out the word and. In our situation, it's only going to be horizontal or oblique asymptotes. Step 3, in order to graph, you need some points. So we're going to find all intercepts, x and y. And at least one point per section, and I'll describe what I mean by that more clearly when we get to our examples. So these are the steps that we're going to use every single time for graphing rational equations. go. Move them there. A little bit off to the side so we still can see them while we do our question. Now the question does say, use the equation of each function to predict its graph has vertical asymptotes or holes. So what they're really doing is saying, we want you to focus on step 1 first. Okay? We're going to do that, but we're going to finish it off by doing everything. Okay? So when we go to graph this, x squared minus 25 over x plus 5, we see right away that this has a non-permissible value. That's not an x. Looks like an x. X can't equal negative 5. So the question becomes, is that non-permissible value a hole or is it a vertical asymptote? We determine that, step 0, by factoring. We have to factor our equation to see if anything cancels out. So our equation, sure enough, our numerator beautifully factors to x plus 5, x minus 5 over x plus 5. Is there a factor that's identical? Yes. These cancel out. And I'm going to write this now in green. Our new equation is y equals x minus 5. And what's our non-permissible value? Is it a hole or is it a vertical asymptote? It's going to be a hole. So we can write out that we know that we have a hole at, our non-permissible value is negative 5, so we know that the x-coordinate of our hole is negative 5. To find the y-coordinate, we take that new equation and say, it's a line. If I plugged in negative 5 for x, I would get negative 10 for y. That's where my hole is going to be. Okay? We are done step 1. We've determined all the vertical asymptotes and holes. This equation only has one thing. It's a hole. Okay? When we get to step 2, so I'll put a 1 beside here because that's what we did for step 1. When we get to step 2, to figure out horizontal and oblique asymptotes, this is where the green note is really important. Okay? After step 1, it says always graph the simplified equation. My simplified equation I wrote in green. Do you know how to graph y equals x minus 5? It's a line. You don't need any of this other stuff anymore because we're now graphing a line. Okay? And it's important that you notice that because if you went to step 2 of the original equation, your brain would tell you there's an oblique asymptote. There is no oblique asymptote in this one. We have to graph the simplified equation, which is a line. And so we don't even have to do step 2 because our new equation is y equals x minus 5. That's something you already know how to graph. And since you already know how to graph it, you can go right away to drawing its graph. It's a line with a y-intercept at negative 5, a slope of 1, so my x-intercept, and we have to add to this line that we have a hole in our graph, so at the point negative 5, negative 10, we draw the hole. So this first example, they were really kind in pointing out that important green part of our notes that says, if you simplify it, you now graph the simplified equation and add the hole to that simplified equation. In this case, the simplified equation was something we already knew how to graph, and we didn't have to go through our steps 1, 2, and 3 because it was a graph we knew. Sometimes the simplified version will still be a rational graph and you still have to go through steps 1, 2, and 3 for that new graph. That'll be fine. But in this case, it was simple. We could graph it right away. Okay, everybody good for graph number 1? I can move it back down. Because I'm going to erase graph number 1. We're going to do graph number 2 while still being able to see the steps on the same page. Good? Okay. Graph number 1, gone. Whew. Part B. Y equals 4x plus 2 times by x minus 2. So step 0, can you factor anything? I can take a 2 out of the top, leaving me with 2x plus 1 and x minus 2 on the bottom. I know that I have a non-permissible value that x can't equal 2. Step 1 says, is that non-permissible value going to be a whole or a vertical asymptote? Does that factor cancel out? No. Since it doesn't cancel out, we know that we have a vertical asymptote at x equals 2. Nothing simplifies, so the green part doesn't come into this at all. We still have the original equation. Okay? Step 2. We need to determine whether we have horizontal asymptotes or oblique asymptotes. Look at our equation. Highest degree is an x. Notice that we have the same in the numerator as the denominator. So in this situation, we have a horizontal asymptote. So we can just write, I know there's going to be a horizontal asymptote, and the coefficients are 4 on the top, 1 on the bottom, which you could have just written as y equals 4. So we have a horizontal asymptote at y equals 4. Off to the side, I'm going to start graphing this, and we're going to put what we know on our graph already. We know we have a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 4. Step 3 says find all of your intercepts and graph at least 1 point per section. So to find a y-intercept, that's really easy. You go to your original equation and plug in 0 for x. If I plug in 0 for x, can you see that I have plus 2 on the top, minus 2 on the bottom? 2 over minus 2 is minus 1. So 0 minus 1 is my y-intercept. And just as a little note reminder here, we find a y-intercept by plugging in 0 for x. Next, you want to find your x-intercept or x-intercepts. Same idea, but now we plug in 0 for y, and we get this equation. 0 equals 4x plus 2 over x minus 2. You can plug it into the original, or you can plug it, and normally I would plug it into the factored one. Now with rational equations, when you plug in 0 for y, you're basically asking yourself the question, when is a fraction equal to 0? Okay? Using real numbers, can you give me an example of a fraction that's equal to 0? Sorry? 0 divided by any, well, pick one. 0 divided by 4. 0 divided by 4 is equal to 0. Okay? 0 divided by, you said any number, because it wouldn't have mattered if you did 0 divided by 7. 0 divided by 73. Whatever number's on the bottom doesn't matter, but the key is the number in your numerator has to be 0. If you want this fraction to equal 0, the numerator must be 0. In fact, algebraically, you could multiply both sides by the denominator. And if I did that, the denominator would just go away. So the nice thing about having your numerator factored, look at the factors. Is 2 ever 0? No. What would make 2x plus 1 equal to 0? 2x plus 1 would equal 0 if x was negative 1/2. And so now we know that our x-intercept is at negative 1/2 comma 0. And that's the only x-intercept because that's the only time our numerator will be equal to 0. So we have 2 points on here, and those 2 points are enough for us to graph one section. Okay? So when I say we need at least 1 point per section, sections are determined or separated by the vertical asymptote. So I don't know if you want to put that the sections are determined by vertical asymptotes. So we have one vertical asymptote that splits our graph into 2 sections. Horizontal doesn't matter. Our sections are determined only by the vertical asymptotes. We have 2 sections. Do you notice that we have 2 points in the left section? We have our x-intercept and our y-intercept are both to the left of our vertical asymptote. We have 2 points in that left section. As soon as you have 1 point in a section, your graph has to approach the asymptotes. So I know, well, these 2 are going to be connected, and this has to go down towards the asymptote, and this will have to go up and bend towards the asymptote. So I know that section. The reason we need at least 1 point per section is to find out what the other part of the graph is going to look like. And I can do that by going just a table of values. Oh, when x is 3, I'm on the right-hand side of that section. So if I plug in x equals 3 into my original equation, 4 times 3 plus 12 would be 14. 3 minus 2 would be 1. I'm going to get 3 comma 14. Where is 3 comma 14? Well, it's way up here somewhere. I'll try my best not to have it go too far up. But I now see that in order to graph this part here, it has to be in that section. So I have at least 1 point per section. I've got 3 comma 14, and I've got x-intercepts and y-intercepts. Sometimes you won't need to find that extra point because your x-intercept is in one section, your y-intercept is in the other section, you're fine. But in this case, we did need to find another point because we need at least 1 per section. And you need to make sure that that point in that section is labeled. Even if you know that the graph is up in that area, if you don't label that point in that section, there's a deduction for that. You have to have at least 1 point labeled per section. Okay, so I'm going to give you questions, but we're going to do example 2 right away. The questions for example 1, or the question for example 1 is just number 5.